So Dana will tell us about local testing, distance estimation, and self-correction of codes.
Okay, thank you, Noga. Okay, so Noga already said the title of my talk. I'm going to talk about self-correction and local testing and related problems, local algorithms for error correcting codes. And this is joint work with Michal Moshkovitz, who's my sister. Okay, so what I want to start with is a very brief overview of error correcting codes, just to set notation, basically. So error correcting codes. Not this one, okay. I'll use this for titles. Okay, so an error correcting code, you take a message with alphabet sigma of length k, and you encode the message into a larger number of symbols over sigma, n is larger than k. And what you want is that if you start with two different messages here, even if they differ only in one symbol, here you get messages, you get encodings that differ in these symbols. Okay, so the parameters are n, k, and d with alphabet sigma. Okay. So there are two ways to define the code, either to say there is this encoding function that takes a message in sigma to the k and gives you a message in an encoding in sigma to the n. Another thing is to just view the image of this transformation, just a set of code words. And basically, I'm going to alternate between the two references to the code. Okay. There are two important parameters. One is the relative distance. This is d over n. The other is the rate. This is distance. And we have k over n, which is the rate. We want the distance to be as large as possible. We want the rate to be as large as possible, meaning that we have a short encoding that manages to separate the code words a lot.
What is the distance?
What's
D is you take two strings in the image of this transformation.
Which came from distinct, okay?
That came from distinct messages here. How much they differ, on how many symbols they differ. Okay, and you want them to differ on as many symbols as possible. This is the Hamming distance. Okay. So there are some basic trade-offs between those parameters. We want both of them to be as large, as close to 1 as possible. They can't be both very close to 1. Their sum has to be at most 1. This is just by counting. Another observation is that the distance is at most 1 minus 1 over sigma. So this is not even tight, but if you want the distance to be very close to 1, then the alphabet should be sufficiently large. Okay, and the notation I'm going to use are, so I have delta to denote the Hamming distance between two strings, and I'm going to have agreement, which is 1 minus delta to denote on how many symbols they're the same. Okay, this is the notation I'm going to use. Good.
Is also relative delta xy, or is this?
This is relative. So it's a fraction between 0 and 1. Okay. So in general, the setting of parameters that I'll want is the following. I will want the size, the length, to be almost linear, which for me means this, and equals k to the 1 plus little of 1. Okay, so this means it's not even concentrate, it's subconcentrate, but it's not much of a blow up in the encoding. Usually we know correcting codes where n is linear in k, but we are going to want more from our codes, and that's why we'll be willing to have this. And we want a distance which is very close to 1, which is fine because the rate is so small. And for this, we'll need the alphabet to depend on epsilon. We mainly care about the alphabet being, function of epsilon and not of n. Ultimately, polynomial in 1 over epsilon. This notation, polynomial in 1 over epsilon, is going to repeat many times in this talk. And we won't care about optimizing the constants in the polynomial, though it's an interesting problem, just the lower order terms of the problem. Okay, so I want to talk about local algorithms for codes. So a local algorithm for a code, so it gets this word W that typically is supposed to be a code word, but maybe it won't be a code word, and then it's only allowed to query a small number of positions in the code word. Typically, we have some parameter epsilon, and this will be polynomial in 1 over epsilon. Okay. So what kind of local algorithms would we be interested in? So one is local testing. So local testing, you get this W, and you want to distinguish between the case where W is in the code and the case the W is far in Hamming distance from the code. Okay. Good.
What do you mean by that code?
You have a code, so we fix some C in sigma to the m, and then we want this C to have local algorithms. I can do all the standard algorithmic tasks that are associated with the code by a local algorithm. And here I'm going to enumerate what kind of tasks these are. So one is this local testing. So this, I think, was started by Goldreich and Sudan in 2002, but basically we had such way before 2002. They just formalized it. So here, another thing is distance estimation. Well, you want to have the agreement of W from the code up to an additive epsilon. So this is some small parameter. So, okay, it's clear. So this is obviously a generalization of local testing. If you can estimate the agreement, it doesn't matter if we're talking about additive approximation, it doesn't matter if I talk about the distance of the agreement. I enjoy talking about, I'm used to talking about the agreement for all kinds of reasons. So if you have an estimate, a very good estimate of the agreement, then of course you can look in local tests. You can know whether the word is in the code or far from the code. So there were many works that started talking, okay, so we have local testing, we want tolerant local testing, they have all kinds of names, and this is generalization of all of them that first appeared in this paper by Michal recently. But again, also this, we actually had codes like this way before Michal tried to just formalize this definition, and there were formalizations, generalizations of this even before this.
So there is no connection between this epsilon and that epsilon?
No, there is. So, so this will be some epsilon, some polynomial in epsilon. Okay. Yes. So, okay. Okay, so this is a generalization of this. Another problem that was considered is local decoding. Local decoding. So here, the problem is as follows. Supposedly, someone took a message and applied this encoding, and then the encoding was somehow ruined. And then, although it was ruined, we hope that there is enough redundancy here to decode, say, the ith message of the input message, the ith symbol, the ith symbol of the message for any I. Okay, using just a constant number.
So you want to do all of these using L1 queries?
What?
You
What
want
all
to do
of
all
these?
tasks with a constant
Yes,
number?
these are. I'm just enumerating
Right.
the tasks we consider, and yes, we'll consider all of them. So this is local decoding. A generalization of local decoding, in some sense, is local testing, self-correcting. So this is Katz and Trevisan first formalized this. So self-correcting means that you don't want to decode symbols of the message, but symbols of the code word that is close to this. And again, we had some constructions of this. Notice that at least when the code is linear, or whenever the code word actually contains message symbols, then this is a generalization of this. Okay, and in linear codes, you can always convert the code, just apply change basis, so the first bits are just the message bits. So this is really a generalization of local decoding.
Repeat the definition of self-correct.
Self-correction means that you get an index here, J, say, and then you read a few more symbols, and then you want to find the jth symbol of the code word that is closest.
Is there just a general reduction that says, look, if we have a locally decodable code, we can modify it to get it self-correct?
No. Yes.
And then to complete the picture, I think there should be an arrow from self-correction to distance estimation.
Yeah, oh, thank you. Yes, so I want to make a few remarks. Of course, I'll get to what. So Russell always says the next, gives away the next slide or the next part of the talk. Okay, so I want to remark something, maybe let's do it here. I want to remark something about self-correction. So self-correction, usually you say, suppose that there is a word that agrees with word C, code word C that agrees with the word W a lot. And what is a lot? It's some parameter. Then I want to output or to decode according to C. Okay? So this is sort of a standard definition of self-correction. I want to also consider the other side, where whenever you decode, it means that the decoding actually belonged to this, is from the C with, well, this is a sloppy notation, but okay. So whenever you decode something, it comes from a code word with substantial agreement. Of course, everything is with high probability. Okay. So here there is one with high probability, and here we have some with high probability. The probability that we decode something that is not from a closed code word is small. Okay. So these are the two sides of this. The two containments. Everything that is close you're going to output, and everything that you output is close. Okay, and this is how I want to define self-correction. What?
Are you talking about list decoding or indicoding?
Yes. Oh, so this is remark number 2. So the question is, what is this T0, the threshold that you're interested in? So there is the unique decoding regime, where T0 is 1 minus, let's call it also epsilon or delta, or very close to 1. And there is the least decoding regime where T0 is maybe some constant in epsilon to some constant, okay? And many times in all those local algorithms, first people consider the unique decoding regime, which is simpler yet non-trivial, and they do something for that, and only as a second step, they manage to do something for least decoding. And we're going to consider the harder, the least decoding setting, okay? This means that there may be many code words that are close to the code. Maybe the word is, here it's C1, and here it's C2, and maybe here it's garbage or whatever. Okay, and we want everything that is close. Okay. So this was remark number 1. This was remark number 2.
This notion of least decoding, it doesn't really agree. I mean, is it consistent with, for example, things like local decoding? Because in a sense, least decoding means you have several candidates, right?
So
Yes.
you have to,
No, but
you have to have some kind of index for the candidate.
Oh,
So
okay.
So
Yes.
it means that you have some, index or randomness, and you decode as far as the ith element. You're given I, and you decode the ith element on the list.
Okay.
And
Okay. I
some
see.
of the elements on the list may be sort of garbage.
Right.
No, so I don't
rejected.
want garbage elements in the list.
But they could be like rejected. The algorithm.
Yeah, I can say the algorithm may say, what I see is not inconsistent, and I reject. Okay. But if everything is garbage, if it's completely far, it's a random word, you don't expect it to do. You expect it to return as an empty list, right? According to this definition. Wait, no. I want to repeat what you said. So what I was asked is if we are allowed to return a list of outputs, and the alphabet is very small, and we just correct one symbol, then what's the point? If the alphabet is binary, maybe I'll always return 0 and 1, and it would be fine. So, of course, this is interesting when the alphabet is large, and this also brings me to the third remark that we'll consider also self-correction for L tuples. Self-correction for L tuples means that maybe I don't want to self-correct only one J here, but maybe I want to self-correct a bunch L symbols here. And then even if the alphabet is binary, if L is large enough, then if you correct lots of them, then it's a non-trivial task. Okay. Good. So these are the remarks I want. Yeah, now Russell's point. And Russell's point was that this diagram where what is a generalization of what is not complete. Self-correction under this definition also gives you distance estimation. Because what you can do, you have your word, or at least self-correction for L tuples, because you have your word, you correct L, which is polynomial in 1 over epsilon, positions from the word according to the code word, and then you just see how much those positions actually agree with the word you got. And this allows you to do distance estimation. So at least self-correction for L tuples, which is what we'll consider, not only implies local decoding, but also implies distance estimation and also local testing. What? Not necessarily, but this was obvious. Why self-correction is a generalization of local decoding was obvious for linear, and it's true whenever the message bits are part of the output bits, symbols. Okay, good. So these are the problems we care about. By the way, notice that one polynomial in 1 over epsilon is optimal if you want an estimate within epsilon. Okay. Good. So these are the problems. And let me give you an example of a code that has all those properties. And in a way, it used to be the only code that has all those properties that we knew of. And this is the Reed-Muller code. So let me remind you what is the Reed-Muller code. So it has a few parameters. One is a finite field f, which will be pretty large. And the others are two natural numbers, d and m. And the code words of the code are all functions from f to the m to f. The code words are the truth tables of m-variate polynomials of degree at most d over f. Okay? So let's maybe, what? Truth table means that it's that the length is f to the m. For each of the points in f to the m, I have an entry, and the entry, the alphabet, is the field. And you just say for each point what's the value of the polynomial. Okay? So we have this. So I won't write k, but one can compute k, the number of polynomials of or log basis of f, the number of polynomials like this. Okay. So why is this even a good error correcting code? Because of the Schwarz-Zippel lemma that says that if we have two different polynomials of low degree, so we always assume that d is much smaller than f, two polynomials like this agree on very few, only on at most on d over f points in f to the m, fraction of points in f to the m. Know that this code is linear, so without loss of generality, maybe there is some subcube here where this is just the message bits. Okay. So why do we have self-correction? And know that if I show you that it has self-correction, then it has everything. So here is the idea. Suppose that I want to know what is.
You call it big fields, fields bigger than the degree.
Yeah. Okay. The degree is much smaller than the field size, and so Schwarz-Zippel can be applied. Okay.
So you don't want to look at binary.
No. It's a very large. I want to consider the case of very large alphabet. No, not very large. Polynomial in 1 over epsilon. Okay. So suppose I have some point in f to the m. I get a function f from f to the m to f. This is a supposed code word in this code. And I want to know for every polynomial that is close to f, I want to know its value on some point of my choosing. Let's call it x naught. Okay. So how am I going to do it? So the idea is to pass a random manifold through x0, and then on this random manifold, just consider f restricted to the random manifold. It's constant dimensional, so the number of queries will be much smaller than f to the m. And I'm going to ask what are all the close low-degree polynomials on f restricted to the manifold. Okay, so I just consider f on the manifold. I find all the close low-degree polynomials. For all of them, I can interpolate to get the value for x0, and I just output all those that are at least, some, t0, t0 close. Okay. So this is the algorithm. Questions about this algorithm? I want to tell you why it's true.
So then, what remains to be done? Like, where does it? What is it missing in the parameters that you want to do better?
Of course, we'll get to it.
Okay.
So the manifold will be of size f to some constant, maybe. So this is the number of queries. The number of queries is the size of the manifold, which is this. F is going to be, well, we'll get to it. This we'll see has to be at least polylogarithmic. We'll go over the parameters, and this is not what we want. We want constant. But we'll get to it.
For this, is there any reason not to pick the manifold just to be a line?
Yes. Or maybe it's true. I don't know how to show that it's correct. Okay, I'll tell you why. So first, let's do it one by one. What's the idea of this? So first of all, if we just consider the easier direction, which is every code word that agrees a lot will show, then just a line is enough. Just a random line is enough. Because a random line is going to contain much of this closed polynomial, and so it will appear in the correction. Yes. So this is fine. But we also want the harder direction, which is all the decodings are from some globally closed low-degree polynomial. And this turns out to be pretty hard to prove. This actually follows from what's called low-degree testing theorems, especially in this list decoding regime. It's pretty hard.
So where is this analysis of the Mueller code from?
Which?
The low talking about now.
Low-degree testing.
It has all these properties of being, giving the vocal testing, the local decoding, and so forth.
So first of all, I only need to show self-correction, right?
Okay, yeah,
but
fine.
yes.
That's
So
the stuff, right.
so the first people that managed to do the list decoding regime were Sanjeev Arora and Madhu Sudan, and also Muli Safra and Ran Raz in '97. Before that, there were works only for the unique decoding regime. Then if you want very efficient codes, then Ran and I had a few years back, this work on that. Okay?
So these are not using the kinds of parameters that you put up on the little...
No. So we're going to talk about the parameters. Of course, if we already knew the parameters I wanted, then there wouldn't have been a talk. So let me talk about the parameters. Okay.
So just to double-check, so here you're not talking about any disambiguating points or anything like that. In your notion of list.
Oh, so what you can do is instead of considering just x0, you can consider x1, x2, x3, x4, and then has some subspace that goes through everything. Mm-hmm. And then you have all of them. This does the disambiguing, right? Because the value of the polynomial on a random point, disambiguates the polynomial. Okay? So just for simplicity, I'll many times just consider what happens for correction of just one point, but actually what we'll need for all kinds of problems like disambiguating and distance estimation and so on is to correct many points. Okay, so let me just briefly discuss the parameters with Mueller, and we'll see why this doesn't give the parameters we wanted. So the parameters, the question is, of course, how you choose M, D, and F. You want to encode K symbols. How do you choose those three parameters? You have more degrees of freedom than you need. What trade-offs do you take? So I'm not going to go over everything, but I'm going to give you the bottom line. So let's do this table. So there is the length of the code, there is the number of queries, there is the alphabet, and the distance. So one possibility, this is the almost linear length, is length which is n times 2 to the log n 1 minus beta for any beta that you want. Okay, so this is not 2 to the log n, but 2 to the log n where the log n is with an exponent of 1 minus beta, so smaller than 1. So this is n times n to the 1 plus little of 1. And then the number of queries can be made 2 to the log n to the order of beta, and the alphabet 2 to the log n to the 1 minus beta, and the distance is 1 minus 1 over 2 to the log n. Okay. So this is one choice of parameters. A different choice of parameters is polynomial length. Then the number of queries is polylogarithmic. And the alphabet is polylogarithmic. And the distance is 1 over 1. 1 minus 1 over polylogarithmic. And okay, so this corresponds to taking a very large field and a very small dimension. This corresponds to taking the field and the dimension to be about the same. And there is always the Hadamard parameter setting, which corresponds to exponential in, I guess here, whenever I wrote n, it's k, right? So exponential in n, and then the number of queries can be constant. Well, let's do 1 over epsilon to the order of n, 1 over epsilon to the order of 1, 1 over epsilon to the order of 1, plus epsilon. Okay. So we can have exponential length and then get constant number of queries, constant alphabet. Okay. Now, of course, you can choose other parameters, but these are the main interesting settings. And as you see, nothing gives what we want. So either it's super constant, but and short, or it's very lengthy and constant number of queries. I want alphabet size. I want the best of all worlds. I want, this number of queries in alphabet, and I want this length. Okay. And with Reed-Muller, I can't get everything. Okay. Okay. Of course, well, no, I'm not going to actually achieve. Okay, so let me maybe. I want this, and I want this. Okay. So I'm not going to achieve all of this, just because self-correction is a generalization of local decoding, and local decoding is a notorious open problem, and the best constructions we have are slightly sub-exponential. Nothing comes here. Also, there is a lower bound for constant number of queries of superlinear length. This is the work of Katz and Trevisan. And for 2 queries, there is even an exponential lower bound, and so on and so on. Okay. So really, what we're going to consider is not self-correction.
Sorry, can you just provide some context, maybe briefly say, if you consider that Heinz construction, so what would be missing for you? I mean, what is not?
First of all, Sergei Hanin's construction doesn't do, I think now it does do list decoding, right, with your works and Amnon and, yes. No, but Sergei did and then Klim after him, it's slightly sub-exponential length. It's slightly better than this, but it's of course nowhere here. And we even have a low bound of Katzen-Trevisan that says that we can't have this.
Right, yeah, we can.
Okay. So, of course, we can't achieve this, and what we're going to do is just not consider the same problem, but consider the problem of average case. Self-correction. So what is average case self-correction? So I have my supposed code word, I have W, and then say I want to correct J, but not only I'll manage to, it's not that I'll manage to correct every J with high probability, but I'll manage to correct, I manage to correct with high probability over J and over my randomness, okay? So most of the J's I'll be able to correct. Okay? So correct with high probability over J and over randomness, and not just over the randomness for every J. And if this is your definition, then there are no lower bounds. And actually, we're going to see a construction with almost linear length. Okay, so the problem is completely different.
But that's good enough for this.
And this is completely good enough for, distance estimation or local testing and all those stuff.
Linear?
What?
The linear code?
Is it a linear code? So the code I'm going to show is not linear, I think. So we haven't finished writing the paper, but we think that it can be made linear.
It can be made linear.
Yes, we think so. We haven't verified it. Yes.
How does this relate to Ben Sasson, Sudan, Matan, Victorson have some relaxed locally decodable code?
Yeah. So this is a different notion. So So okay. Those guys, BGHSV, Ben Sasson, Goldreich, Harsha, Sudan, Vadhan, they considered something of this flavor. So the important thing is that they only consider the unique decoding regime, okay? And because they consider the unique decoding regime, this definition doesn't make much sense. I think in the unique decoding regime, why is that? Oh, because in the unique decoding regime, if you know that you have a code word, only just very few of 1% of the code words are fine, then with probability 99%, just the thing itself gives you a good correction. Okay, so in the unique decoding regime, this doesn't make much sense. Okay, but they did want to consider some average case notion. So what they did was to say, we're going to do testing and decoding, and the decoding will be for every J with high probability. Either we say we don't know, or we say the correct answer, and so it's the decoding is worst case, but the testing is average case or something of this. It's a very twisted definition, in my opinion. Maybe I shouldn't say this when it's videotaped. What?
In the unique decoding regime, you may also want maybe to correct with higher probability, right? So maybe it's 99%.
No.
correct, but I want to be
Yes, that's
correct
true.
with probability
Yes.
1 minus epsilon for much smaller epsilon.
Yes, but I don't think that they can do it. So in any case, they chose, because of this problem of the thing itself, the message itself, if it's only corrupted a little, then it's already a good correction. This is what they explain why they chose their definition, which frankly I don't, somehow it's not clear in my head now, but I think it's a bit weird. It's a mix of average case and worst case. Okay, all those notions, they've been, local algorithms for codes have been researched in our community for the last, 20 years more. So there are many constructions and many notions that were introduced, and I just choose the ones that I like. Okay, more questions? Yes?
So for linear code, at least for self-correction, there's a very clean algebraic way to define them as having many small
This is not true for the average case.
Yeah, so for
What?
the average case, there's no way to characterize the codes using the dual distribution of flow weight words in the dual.
So,
I mean, the set with high probability over the index, I mean, it can be always the same set of indices, right? You can have a fixed set of indices that
yes,
you
there is.
succeed on.
Yes.
So it's always the same set
Always, you mean always over what?
for every.
After we fix the W,
No,
or what?
no. For every W, it could be the same set of indices that you succeed on.
For each W, there are the indices you'll manage to correct, and there are the indices you won't manage to
Yeah,
correct.
asking if it's possible that it's the same set always for every W.
For all W's, it's the same set of indices, or no? It depends on the corruption, of course.
Right.
What you will manage to decode depends on what was corrupted. Okay, so I barely have time. Okay, so for this relaxed notion, which I find very natural and definitely suffices for these applications, and I think it's a
Distance estimation and local testing.
yes.
That's the main goal, right?
What?
That's the main goal, to do distance
To do-
estimation. Well, this is not,
I think average case self-correction. I think, to me, in my opinion, this is the right definition. For me, the definition of worst case local decoding looks like too much to ask for.
Well, sometimes I'm trying to think about, maybe it's a silly question, but is it obvious that if you assume for a second that your goal is distance estimation, is
Okay.
it obvious that this transition is lossless? I mean, aiming to the best possible self-correction, you don't.
No transition.
I mean, going to.
This is actually self-correction is stronger
So is it
than
proper, or
than
is it
it's stronger than
lossless
yes.
stronger? You
No,
don't
it's
lose-
stronger.
I mean, you don't lose.
I don't know. I don't lose into parameters if I don't care about the constant in the 1 over epsilon.
Okay.
So I'm going to get the optimal. If I don't care about the exponent, I'm going to get the optimal parameters. Okay.
So the argument though that self-correction applies local decoding sort of doesn't, you're not
No,
necessarily
I'm
gonna
al-
get the-
I'm also going to get average case local decoding,
Oh,
of
yeah,
course.
that's a separate
Yes.
thing that's not, doesn't fall from average case self-correction, that's.
Average case self-correction, if I can choose what are the symbols that I want to correct, gives local average case local decoding.
I see your algorithm is dependent on the symbols that you want to find.
Yes.
Okay.
Yes.
That, all right.
Mhm.
So this is kind of like Zed's question a little bit.
I'm not sure that
No,
it is, but
I'd
I'd actually like to see the construction.
yes, good. Okay, I just need another. Okay, so I'll tell you what was the starting point of this work, and the starting point was PCP. So. So let me remind you briefly what is PCP. PCP. I have suppose I have variables of a SAT formula. I have the SAT formula is phi, and the PCP theorem says that there is an encoding such that the encoding I can query a constant number of positions, and then just by testing them, I know whether there is an assignment here that satisfies phi or there isn't. Okay? So I just want to tell you where this comes in how this relates to those. And of course, the problem is that it's kind of apples and oranges. It doesn't relate, and only because here there is a phi, and there, which is an arbitrary, say, linear size Boolean formula, and here there are no phis. Okay. So what I can do is define variants of all these that also incorporate phi. Okay. So what does it mean? It means that I have some phi, and then I only want to correct from code words that correspond to messages that satisfy phi. Okay. So under if correction or testing or whatever are only from code words, say C of x, where x satisfies phi, then I can say that PCP is really in the bottom of this drawing, right? Okay, so maybe I'll do it. So I have self-correction, and I have distance estimation, and I have here, this is average case, self-correction and local decoding, and so on and so on, and local testing, and really PCP is in the bottom of things. If you manage to have all of these with this variant, then you also have a PCP. Okay?
Wait, so again, the parameters that you're going for this construction are the ones that you circled in pink over there?
Yeah.
Okay.
Okay, these also. Right? Here are the parameters I want to have. Okay? So PCP is in the bottom of this thing. It's the weakest thing. And in 2008, so Ran Raz and I had this work that managed to do query reduction for PCPs. And the starting point for this work was to say, okay, so we managed to do it for the bottom of this hierarchy. Can we do it, up there? Can we do it, say, for self-correction? And this is this work, okay? Now, so there was this conception. Well, there were those thoughts in PCP that if you have something for PCPs, then you also have this for local testing, locally testable code at least. And so it wasn't really formalized, but this is the feeling that people in the field had. And what we found from trying to do this was that really this technique that Ran and I had in our 2008 paper, it really shows why it's not true. Why the fact that you can have something here, it may as well fail completely up here. But eventually, with the intuitions that we had and so on, we could do self-correction. Okay, so yes, so what I planned to do was to show you what we did in the PCP and why it doesn't work and so on. But let's not do it. And let me show you the construction. So the technique that Ran and I had was called composition. Maybe I will show you this. So the analogy that I find most helpful is that of concatenation in codes. So suppose in codes you have a good code, only it has a very large alphabet, much larger than you want. What do you do to reduce the alphabet? You just encode each of the alphabet symbols with an inner code, okay? And even if you use exactly the same code that you had here, if here the alphabet depended on n, here just because the n is much smaller, you're going to gain something, okay? And then you can repeat this maybe and so on and so on. Okay, and of course, you can always put a mard here if sigma is small enough and immediately get a constant alphabet and so on. And yes. So I won't show you the old composition, but show you the new composition. So again, we have an outer code and an inner code that are basically almost the same. And the outer code maybe has small alphabet, but it has a very large number of queries. Okay? So what I can do is I can put all the possible randomness strings here. And for each randomness string, I'm going to just map it to the queries that the algorithm does on these randomness strings to the code. And the problem of the outer code is that, like, read Muller, is that here we have a huge number of queries in this construction. The number of queries is just barely sublinear. Okay.
So the outer code will be read Muller.
The outer code, in the beginning, would be read Muller. Oh, actually, always will be read Muller. Yes. And we want to reduce the number of queries of the outer code, and we'll somehow want to do it by encoding these with the inner code. Okay? At least with this variant of the inner code that can check that here we really have whatever property should happen here. Okay? The only problem is that if I just encoded it with the inner code, and even if I had done what we did for PCP, it's not going to work. We don't have time to show it and explain why. But here is our construction. So per symbol, per position in outer code, we're going to have a block. Okay? So code word will be composed of many blocks, one for each symbol in the outer code. Okay. Now, an observation that we had from PCP that does carry to this setting, and we're going to use, is that without loss of generality, we can assume that the degree here is small. The degree here is only polynomial in 1 over epsilon. And this is because there is an easy transformation that makes this happen. Okay? So let's assume
The degree of the hypergraph.
the degree of the graph. This is a graph, a bipartite graph between the randomness and the symbols, and the degree here.
Right.
The number of randomness strings that query each symbol is going to be just polynomial in 1 over epsilon. This is true. And what?
The code changed from read Muller to something slightly different potentially. Or for
Yes.
read Muller it is.
Yes, it's going to be a repetition. No, it's not true for read Muller, but it's going to be some repetition of read Muller code. So each point will just appear many times, and each time will query a slightly different subset. Okay. So we take a symbol in the outer code, and the symbol in the outer code, say this, has a poly 1 over epsilon randomness strings. Okay, so let's write here the neighbors, the poly 1 over epsilon neighbors of the symbol. Okay. And for each one, it's something like this. There is the window that it queries, and what we're going to do is to encode. This is the inner encoding of the view of the randomness string. Okay, and I'm going to do this per each of the neighbors. And the way I'm going to parse this is that each alphabet symbol is just this column. Okay, so the alphabet is the alphabet to poly 1 over epsilon. However, you can always decrease the alphabet just via concatenation. This is just easier to consider this. The length is going to be the length of the outer times the length of the inner. And what about the distance? How good is the distance here? So I suppose that I have two different code words here differ on many things. But the issue is this: if they differ on even some significant fraction, most of the neighborhoods are going to be, and this graph is a good sampler, say, then most of these neighborhoods are going to differ a lot. And after we encode, they're going to differ even more. So if the graph is if graph is sampler, if the graph is a sampler, then basically all that matters is the inner distance and not the outer distance. So this is this version of concatenation where the distance is not the multiplication of the inner and the outer. So we don't lose here, but we actually inherit. If the graph is nice, then
What does it mean for the graph to be a sampler?
it's an expander. Some good expander, yeah.
It's a little bit similar to what we were doing for
I'm sure that it appeared before in the coding theory literature. It's so vast and that. But which paper is it?
with this Ronnie Roth and Shuki Brook and
Okay, ABN and.
right.
Similar to the tenor.
Yeah. Actually, it's expander codes, right? So it's the same expander codes that.
In fact, if you pick any 1/epsilon papers from the coding theory, you can recover this notion.
Yes. Okay. Good. So yeah. So let's just say briefly why this works. Okay. So there are to show self-correction, we need to show two things. One is the easier thing, that if we have, if this is close to a code word, then we'll correct according to this code word, and the other is the hard direction, where all we correct is from, some global code word.
So to begin with,
Oh,
sigma is pretty big, but then you reduce it by further concatenation?
Yes, we can always reduce sigma by concatenation. Yeah. So this is a good point, yeah. Okay. So let's start with the easy direction. How do we do self-correction here? So the issue is that each layer here doesn't appear just once; it's going to appear many times for all the symbols that are in here. And we're going to use this property of those codes that the encoding only depends on the message and not on what we want to correct. Okay, which holds. The only thing that depends on what we want to correct is what we observe inside the code. Okay. So in general, the main idea is that we're going to correct each one of these by consulting poly 1/epsilon of the occurrences of this layer, taking all the corrections that repeat at least epsilon fraction of the time. These are corrections that we can count on. And each layer like this, it contains the symbol here. So we'll always correct also the symbol here, and we're going to compare on this symbol. Well, I barely have time.
High level?
No. So this is the high level. So right, each layer is going to correct several symbols, including the symbol of the block. Okay, and then to correct, it's going to consult its friends, and then to match between these, it's going to compare on the symbol of the block.
It's list decoding, so
And it's
so
list decoding.
this image.
Yeah. So that's the outline. Yeah.
Okay, the paper exists?
The paper hopefully will be written, is written, but will be finished soon. Yes. So, yes, and I should say that there are some complications since we want not to correct just one symbol, but many symbols, and we somehow have to, they all have to come from the same code word. So, so we have to also compare something along layers, but that's the main idea. Yeah.
So this uses a PCP unit?
Yeah.
So there is a PCP which one takes and uses as a gadget within the construction.
Yes.
So like
Because I want this version where corrections, the inner corrections should only come from something that satisfies the property that this should satisfy.
so it's a PCP.
So it's not a PCPP, it's something that implies a PCPP, but is
But the
yeah.
PCP you need is the strong one from your paper with Ron, or
No, so it's right, a bad PCP,
Oh,
right? That
bad.
it's a Reed-Muller-based PCP that has large number of queries, and but we reduce it so we don't care. Yeah.
And
Okay.
So, okay. So wait. So PCP had been used before for error correcting codes. Like I guess if you wanted the one. With
If you want local
all
testing, all the constructions of local
Yeah.
testing of all those stuff always use PCPs, or not always, but traditionally use PCPs. Okay.
So there was BSVW in your earlier paper with Ran that gave linear length locally testable.
BSVW only give unique in the unique decoding regime.
Oh right.
That's the important.
Oh right. And then yours made it your paper with Ran, not the PCP one.
The low degree testing one is with a large number of queries, just because it's just a Reed-Muller.
Oh, and there you didn't make a PCP out of it? I thought
Yeah, we did make a PCP out of it, but not right. As you see, we needed a different ideas to get self-correction and local testing and so on. Okay. So I apologize for the hasty ending because we have a train to catch. But thank you.
Okay.